Tiziano Passerini, who's going to talk about multiscale modeling for vascular networks.
Okay, so good morning. I would like to thank the organizer for inviting me and giving me the opportunity of presenting my work here. I'm currently a postdoc researcher at Emory University in the group of Professor Veneziani, and I was formerly a PhD student at Politecnico di Milano, at MOX here, in the group of Professor Quarteroni. And the motivation of this work was the study of cerebral aneurysms. So I will give you a brief idea on the motivation of this work, and I will show you that the strategies we used in this project actually can be extended to the study of other arterial networks, such as, for instance, the coronary arteries, or in general, arterial network in which we are interested in the interplay between local blood flow features and global blood flow features in arterial networks. So here the point was find a way to model the interaction between these two different geometrical scales. So I will show you the models we used. I will focus on the a particular model for the interfaces between heterogeneous models we used, and I will show you some results. So regarding the description of the global blood flow features, we used a one-dimensional modeling for arterial network, which is quite used in the literature because it's based on this set of equations, the Euler equations, which turn out to be a system of hyperbolic equations whose the solution of this system is expressed in the form of traveling waves. And this form is particularly interesting for describing the pulse wave propagation phenomena in the arterial network. So here you see a sketch of an arterial network including the circle of Willis, and here you see the propagation of a pulse wave in the arterial network. So the idea is that we want to couple that global description to a more local description based on the Navier-Stokes equations, in which we are interested in the detailed description of the local blood flow features in terms of pressure, velocity, and wall shear stress. The application we have in mind is the description of the wall shear stress solicitation, so the shear load exerted by the blood on the arterial wall, and how this value is associated to the location and development of pathologies. So here you see the wall shear stress map on the arterial wall of an internal carotid arteries, and its distribution along the curvilinear abscissa. And we found out in the aneurisk project that this kind of analysis well correlates with the location of the pathologies in the arterial network. So the general idea is that you have a global domain of interest, and you split this domain in two different regions. And in one of the two regions, you used reduced modeling. So because the idea is that it's usually you have large arterial network which you are interested in studying, and three-dimensional modeling of large arterial network is not feasible due to high computational costs. So another advantage of geometrical multiscale modeling is that you have an effective description of the network, but reducing the computational effort. So when coupling these two different models, you have to face two main issues. So the fact that at the interface you have to exchange information, so you have to express the boundary data according to the features of the models you are using. And then typically, in order to get the global solution, you have to set up an iterative scheme, so solving the blood flow problem in each domain sequentially, and then finding the global solution in an iterative manner. And in the specific case of 3D 1D modeling, we wanted to prescribe the conservation of physical quantities at the interface, namely the continuity of total pressure and the conservation of mass. And in the two different models, these two quantities are expressed in different ways. So here you face the issue of the boundary condition prescription. You have to do suitable hypotheses on how to exchange information between the two models. And this approach can be usually effectively used for for instance, the downstream dynamics of the arterial network and its effect on the three-dimensional solution here. So when using this approach of the continuity of physical quantities for describing this situation, we get reasonable results. And the other thing I would like to say is that at this stage you could also include, for instance, autoregulation modeling. So the effect of the downstream circulation could be also modeled by an autoregulation model here at this level. So in general, what you want to do is to take into account patient-specific geometries of arterial network and their influence on the local solution. And a problem we faced is when trying to embed the three-dimensional model in a large arterial network. So when dealing with this problem, so now the inflow boundary condition for a three-dimensional model is given by a one-dimensional model. And in the typical setup, you have a mismatch in the description of the arterial wall mechanics in the two models. So usually here we use a three-dimensional model including the hypothesis of rigid walls, and this is because of two main reasons. The first reason is that it's hard to find reliable and validated models for the arterial wall mechanics. And the second reason is that actually the rigid wall hypothesis is quite used in the literature, and it has been shown that it can give significant results and keeping low the computational costs with respect to models including the arterial wall mechanics. But physically, this situation corresponds to the fact that you have a signal propagating into a compliant domain here and facing a rigid or stiffer domain here, so you get wave reflections at the interface. So what we thought, maybe we can take into account the effect of the compliance of the three-dimensional model in a lumped parameter way. So modify the description of the interface in order to gather at the interface the effects of the compliance of the three-dimensional model. And in a general framework, at the interface you can set up a lumped parameter model based on this kind of equations, so including also resistance and inertial terms. And by using this approach, we were able to find promising results in simple geometrical cases. So in this case, we modeled a cylindrical vessel split into two parts, and the one-dimensional model was transmitting a sinusoidal flow rate in this case and a square wave in this case. So we compared a fully one-dimensional solution, which is the thick dashed line here, with the lumped parameter description of the interface in a geometrical multiscale setup. And actually, the solution we got was totally superimposed. And what you see here is the solution we get when using the standard multiscale approach. So in this case, the signal at the interface is really distorted and gets reflected. And we wanted to get rid of this reflection because these reflections correspond to backward propagating waves, which affect the accuracy of the solution in the one-dimensional network. We tried also more complex situation in which we have coupling inflow and in the outflow sections. In this case, we have to work on the accuracy of our model, because as you see here, we have a bit of dissipation, which we believe is due to the numerical approximation. But still, we are able to get rid of this distortion of the signal. And following the same idea, we tried also with more realistic geometries. So in this case, you see that again, comparing our results, our geometrical multiscale model towards fully one-dimensional models, we are trying to find the optimal set of parameters, giving the more similar results. And we tried also our geometrical multiscale model in comparison with the geometrical multiscale model, including fluid structure interaction model for the wall. So in this case, we get, let's say, the qualitative behavior at the outflow, but we are quite satisfied with the inflow, because most of the signal is propagated and not reflected, even if the inflow signal here was chosen in order to be really fast. so just to try how the interface worked here. So I think this is pretty much what we did. What still remains to do, so the choice of parameters affects the effectiveness of the method and the accuracy of the results. So we plan to do a sensitivity analysis in order to understand exactly the role of each parameter in the coupled solution. And maybe one possible extension is try to understand if this lumped parameter description of the arterial wall mechanics in the three-dimensional domain could also be able to take into account other features, not only the elasticity of the wall, but maybe also the viscoelasticity. And then we plan to use this approach to describe a larger arterial network, and in principle also closed-loop networks, including also the capillaries and eventually also the venous system. So this is all. And thank you very much for your attention.
When you were trying to choose these boundary conditions so that you couldn't get reflection, was that for a specific wave, or did that work across a whole spectrum of frequencies?
No, we tried just for those two signals for now. So we chose those two because the sinusoidal with that kind of frequency is representative of an average signal propagating into the arterial network, and the square root, the square wave, just to test also higher frequencies. But we didn't do a specific analysis based on the changing frequency of the signal.
You said that one problem arises from the fact that the 3D model has rigid walls and the more distal 1D model has compliance. If you say that for the larger vessels a rigid wall approach is giving good results, why don't you use a rigid wall approach for the small vessels too? Because I think the relative stretch in the small vessels is really very limited.
Right. Here the idea is that you really use two different models because you are looking at different features. So when you use a one-dimensional modeling, a one-dimensional reduced modeling, you are looking at the propagation of the wave. So this phenomenon requires a fluid structure interaction model because it's driven by the interplay between the flow dynamics and the wall mechanics. But describing these effects in the local model would imply that you really need then to be accurate in the description of the wall. If not, you are misinterpreting the dynamics, and maybe you get wall shear stress values which are not the right ones. So in the local model, you are really interested in, for instance, in the wall shear stress map, which means you are looking at the detailed local description of the blood flow. And this can be really affected by a non-correct description of the interaction between the fluid and the wall.
Okay, thank you very much. So before we go, I realise we're over time, but we have the presenters of the posters for the poster session. We've each been given the opportunity to speak for 2 minutes, and we're a little bit tight on time anyway. So if possible, can we all come back